The last we talked in section 1.1, talked about what does it mean that an equation is called a differential equation. And then we looked at very simple terminology in terms of classification, order, or linearity. And then here, lastly in this section, there are a few problems that are given you so that you can basically verify the solution. I will show you some of these problems, and when we look at them, what I want you to see here is something that you see but you don't see, but I want you to understand that later on we'll be able to actually solve these problems from scratch. So it's a differential equation, and they've already given the solution, and they just want you to verify the solution. Now eventually we will walk through the steps in terms of how to actually solve these differential equations and to get the solution that they tell us. And elementarily, we talk about the solution type, that for certain problems, how they're addressed, the solution type models a certain a skeleton set. And so we'll look at that solution type, get the solution, and then you can easily check to see if that solution is indeed correct. So let's look at a few more of these, and then we'll go to the next section. We looked at that first one there. Let's look at this one here. So here they give us the solution. We have y prime equal to 25 plus y squared. And so they said that the solution is y equal to 5 tangent 5x. So here, we are given the solution. Well, to verify it, we find y prime based on y. So here, y prime is 5 times secant square 5x, then times the derivative of 5x, which is 5. So we get 5 times 5 gives us 25 secant squared 5x. So we replace in the equation the y prime with 25 secant square 5x, and then replace the y with 5 tangent 5x. So we have 25 secant square 5x. Is that equal to 25 plus here the y squared? This is 5 tangent 5x, all to be squared. So we get 25 secant squared 5x is equal to 25 plus 25 tangent squared 5x. All right. So you can divide through by 25. Leaves us with secant squared 5x is equal to 1 plus tangent squared 5x. And by an identity in trigonometry, that's the same, right? Well, we know that cosine squared x plus sine squared x is equal to 1. Dividing through by cosine squared x, we get 1 plus sine squared x over cosine squared x is equal to 1 over cosine squared x. So this is 1 plus tangent squared x is equal to secant squared x. And so that's what we have there. Likewise is the case even for that next one. Let's look at a different type of problem. Here, find the values of m so that the values of the function y equal to e to the mx is a solution of the given differential equation. Now, I want you to look at this problem and look at the next problem here, y double prime minus 5 y prime plus 6y equal to 0. Look at the similarity of the first problem, the second problem, and even also the third problem. And based on how these differential equations are written, their solution has a certain form, y equal to e to the mx. Now, what are they saying? Now, you can't see it, but I pointed out, and then when we get to those problems later on in chapter, I think it's chapter 4, we'll go into detail with it. Now, those three problems, if you look at them, they have something in common. Well, one, they're all linear, right? And then secondly, the coefficients are all numbers. The coefficients are all constants. Do you see that? That's the key. Like the coefficient here is 1, the coefficient there is 2. The next problem, the coefficient is 1, negative 5, and 6. 2, 7, and negative 4. For linear homogeneous, let's set t equal to 0. Linear homogeneous differential equations of order n with constant coefficients, coefficients are constant, the solution type is always exponential. That's what that means. Y equal to e to some mx. That's an exponential form for the solution. So you want to be able to see that. You don't see it now, it's fine. I'm telling you in advance. It's almost like, and I think I talked in the linear class about you go through first grade to the 12th grade, and you probably never talk about the fundamental theorem of algebra. You know, and some of you are like, who? You know, and then maybe perhaps in college you may be introduced to that very powerful classical theorem, the fundamental theorem of algebra. Well, by all means, in calculus, you saw and you were given the fundamental theorem of calculus. It's part 1, part 2. And then in calculus 3, which you don't need that here, but in calculus 3, there was the fundamental theorem of, for those who had calculus 3, what was that theorem called? See, that's the thing. I almost said, whoever had calculus 3, what's that theorem called? I forgot it. Put your hand down. Right? Okay. That's important, guys. That was the last chapter in calculus 3, which is the foundation for vector analysis. You were studying how to compute a line integral. That was the key. Why is a line integral important? Because electricity travels along that circuit line. That's the same thing. So in EE, that's what you're going to be focusing on. Well, also in mechanical engineering, when you're dealing with fluid flow, it's the same line curve. Right? So to calculate the amount of fluid that's flowing along a path or within a tube, right? You call it the flux. Same problem, same mathematical fundamental problem. So we talk about the fundamental theorem of line integral. But in calculus, you talk about the fundamental theorem of calculus. But in algebra, there's a fundamental theorem of algebra. Now, why do they say fundamental theorem? The reason why they say fundamental theorem is that that's what you're supposed to be given first. And then everything else that you do after that makes sense. But a lot of times in algebra, who ever heard of the fundamental theorem of algebra? What? You know? And some of you looking at me like, well, yeah, who ever heard of the fundamental theorem of algebra? But did you also know there was a fundamental theorem of arithmetic? We didn't get that in kindergarten or first or second, third grade. Well, you should have. Because it makes all of math make sense. Now, I had a problem when I was in school. When I was in first, second, third, fourth, fifth, I had a problem, 6th, 7th grade too. Had a problem. I didn't do well. The reason why I didn't do well was because nobody explained to me the purpose of why I was there. And so since they didn't tell me that, I did other stuff. Now, I heard what they were saying. I got it, but it didn't make sense because I didn't have purpose. And I've been talking at the church about the same thing. What's your purpose? What's your purpose to live? What's your purpose to do what you do? Is your purpose to get an education? Well, that's not good enough. Is your purpose to get a career and have a good job and have a big house and a nice car? That's not good enough. That's very small. What's your purpose? Your purpose is big. Right? So the purpose of mathematics, the purpose of why I'm studying this information, it has to go somewhere. As a fundamental theorem of arithmetic. Do you know what it says? Now, you know what it says, but you probably didn't know what it was actually called. That any number can be written as a product of its primes. Remember that? So you take 9, you say 9 is what, 1 times 3 times 3, because 3 is said to be prime, right? Take 24, you break it up. You can say, well, that's 6 times 4, but 6 is not prime. 4 is not prime. So 24 can be broken up as 2 times 3 times 2 times 2. Those numbers are prime. It's called the fundamental theorem of arithmetic. The fundamental theorem of algebra begs the question that any function of nth degree has at least one zero. The fundamental theorem of algebra. Any function of nth degree has at least, and then it talks about the domain and that kind of thing. And so if it's difficult to find the zero, what's the zero for a function anyway? What does that mean? If I got the zero of the function, that says what? In terms of the graph. Thank you. Thank you. The zero of a function means where the graph crosses the x-axis. Right? Fundamental information, but makes a lot of sense, because if you're just sitting there doing these numbers and I don't know what the heck I'm doing, my thing is don't even do it. And I'm telling you, when I was in the first, second, third, fourth, fifth, sixth, seventh grade, no teacher told me why I was doing what I was doing. So I said, okay, I'm just going to sit up here and draw. You know? Steal and whatever else we did when I was coming up, didn't know any better. But when it was told to me, this is what you're doing, this is why you're doing it. Thank you. Get it now. I'll do it. Right? So here, it's always good with looking at a problem to know what's behind it. So if it's a linear differential equation and the coefficients are numbers, then my solution type is always exponential. And we'll go into why that is later on. Now compare that to this. Look at this. You know, the Bible says that wisdom is the principal thing. And here's what's important, even about that scripture. If you don't even believe in the Bible, the scripture is right. Wisdom is the principal thing, therefore get all they get and get to understand it. Right? So why am I going to spend all this time in a class, whether it's online or face-to-face, and I'm trying to learn something, but I don't understand it? You're wasting time. You know, in that regard, you know what I prefer to do? Every day when I walk out and I see these guys out here cutting grass, I'm like, man, this is where I want to be. That's cool stuff right there. And I was like, man, you're outside, the air feels so good, you know. That's living right there. I grew up on the farm, man. Hey, that's it. And inside a building and, you know, it's fake air. You know, you just keep on, you know, talking about whatever else you don't like about the inside, you know, and the outside. Now, I can say that because I'm on the inside comfortably, right? If I was out there every day probably doing that, I'd probably be saying, I wish I can go inside, you know, and get some fake air, right? But anyway. What's up, Michael? Oh, man. But, and I know I'm right. Do you not know that? I'm going to be done with this, and I'm going to get back over here. You can tithe and don't believe and still be blessed by tithing. It's the fundamental principle. This is a fundamental principle of God that he put in the earth. Right? Take a seed, plant the seed, it's going to produce something. Right? That's the principle of sowing. Right? If I sow something, I expect a return from it. But if I give, expect a return. Give, and it shall be given unto you. Good measure. Right? Why do you think that some of these people in the world, some are atheists, some don't believe in God, and their wealth has accumulated so vastly? If you also check what they do, they also give a whole lot. You know? Now they're giving compared to, you know, what amount of money I have, maybe about the same, but they're giving. They are giving. You know, this man may be a billionaire. He's giving millions, you know. I may be a dollaraire, and I'm giving a dime or a nickel or a quarter, you know. But, you know, it may be, racially it may be the same, but I tell you what, they are giving. And in their giving, they're reaping the return as well. Anyway, okay, I'm off that. Look at this. Look at these problems. This is x times y double prime plus 2y prime equal to 0. Look at the next problem. That's x squared y double prime minus 7x y prime plus 15y equal to 0. Now these problems are indeed linear. Their coefficients are x values in nature. It could be x or coefficient, constant for the coefficients to be linear. But the thing about the coefficients here is that there's a variable in front. There's not just constant coefficients like the previous problems, right? Look at this next problem. This probably explains a little bit better. This is x squared. That's x, and then there's no x there. Right? Matter of fact, I mean, the problems, we call them, they're rigged in that they were fixed up to look like something. They're fixed up to look like what? That there's an x value associated to each y. And if it's y double prime, then the x value is x squared. Right? If it's y prime, the first derivative, then this is x to the first power. Well, if there's no derivative, there's no x. Right? Now, when you have a differential equation of that form, same way up here, what will you say? Well, you just said that if it's y double prime, you got to have x squared. If it's y prime, you got to have x. Well, there is an x squared and an x there. It was just divided out. Right? You can multiply by x to that whole equation. You still get x squared y double prime plus 2x y prime equal to 0 times x, which is still 0. Right? So when you have that type of problem, that type of format, then the solution is said here to be polynomial in nature, y equal to x to the m. So it's okay if you don't see that now. We'll talk about it in detail when we get to it, but I just want to try to give you some behind the scene in terms of what's actually going on. You want to get the understanding. Okay, let's go back and look at the problem. So here, if y equal to e to the mx is assumed to be the solution type, let y equal to e to the mx be the solution type. Then y prime is equal to m times e to the mx. We only have one derivative, so we can stop there. The second problem, we have two derivatives. So I'm going to replace y prime with m times e to the mx plus 2 times y. Y is said to be e to the mx is equal to 0. Now look at this equation. I can factor out e to the mx is common. So e to the mx is factored out. I have left m plus 2 is equal to 0. Now, if I have something times something else equal to 0, I set each of those somethings equal to 0 and then solve for the something. So this is e to the mx equal to 0. Or m plus 2 equal to 0. Can e to the mx equal to 0? For any choice of x, or for that matter, for any choice of m. Can e to the mx equal to 0? Can e raised to any power equal to 0? You probably get close to it, but no. Right? Since e to the mx is not equal to 0 for any choice of x is said to be real, this implies then that m is equal to -2, this part right here. So what does that mean? That means here that the solution for this problem is y equal to e to the -2x. Simply check. If y is equal to e to the -2x, y prime is -2 times e to the -2x. Go to the original equation. Y prime is -2 times e to the -2x. This is plus 2 times y, but y here is set to be e to the -2x. Well, indeed, that's equal to 0. So this is indeed the correct solution type. Now, likewise, for the second one, let's see. Let's see what happens. So, yes, sir. Over here. So that means that since this part is not equal to 0, so m plus 2 has to equal to 0. And if m plus 2 equal to 0, that implies that m is equal to -2.
I know, but that little section in the last line that your cursor's on, in the middle,
Right here? Oh, I'm sorry. Bless your heart. You're exactly right. Since e to the mx is not equal to 0, this says for all x that is an element of the reals, this implies that m is equal to -2. That's a mouthful. Okay, better write that out. Maybe we'll put it in red. Red. For all is an element of or belonging to. A lot of our mathematical symbol, Greek symbols, comes from Latin, and then even in that there are derivative symbols that come from Babylonian scriptation, Chaldean writing. So is an element of, belongs to, is actually the depiction of a mother giving birth to a child, that the child belongs to that from which it comes from, is an element of, or it belongs to. Right? And you know that this is the set of reals. The set of all real numbers. Okay? Thank you. So here, the assume that y is of this type, e to the mx. Here I have two derivatives, so y prime is equal to m times e to the mx, and y double prime is equal to m times m, or m squared, times e to the mx. So I replace y double prime with m squared times e to the mx. This is minus 5 times y prime. Y prime here is set to be m times e to the mx, and plus 6 times e to the mx is equal to 0. So notice here that you can factor e to the mx from all three. We have e to the mx taken out. I have left m squared minus 5m plus 6 equal to 0. But since e to the mx is not equal to 0, that implies that m squared minus 5m plus 6, we set that equal to 0. So here, this implies that m squared minus 5m plus 6 is set to equal to 0. So we can factor that. M minus 3 and m minus 2 equal to 0. So we get m equal to 3 and m equals to 2. That's the set notation for and this statement here is this implies that. Right? The inference implies a conclusion. So we conclude that y sub 1, too much. There are two solutions here. So y sub 1 is equal to e to the 3m, and y sub 2 is equal to e to the 2m. Well, the 2x, excuse me. There should be an x up there. The m is the 3 and the m is the 2. Sorry, I get kind of carried away sometimes. Okay. All righty. So I think you have that, understand that. So basically all we're doing is just verifying the solution. Right? They give you the solution type. Can you find the solution based on the solution type? Now later on, we won't even make mention when you're solving a problem like these. We won't even say assume y equal to e to the mx. You will know to assume that based on how the problem is set up. Right? It's a linear differential equation, and the coefficients are numbers. If the coefficients are numbers, then the solution is always exponential, e to the mx. And look at its counterpart. If you have kind of very similar setup, but I had a ruler in here. What happened to my ruler? Oh, there it is. Very similar setup, but here the coefficients are variables with respect to x, like this x times y double prime, then plus 2 times y prime. The second one, this is x double prime times y double, well, x squared times y double prime minus 7x, right, times y prime. So we got some x values as coefficients. Let me work the second one. Here we make the assumption that the solution type is of the form y equal to x to the m. we'll do that, and then we'll try to introduce after this some mathematical models, something that I think you would enjoy. Yes, sir. Daniel? No. Oh, yes. It's a whole lot of others out there. Yes, sir. Yeah. But when you have your baby, you don't give your baby differential equations, the first week that they're born. You give them a little ball or a little square and let them they'll model that and kind of play with that. So we're taking our time with the circle and the squares, right? Which is important because the baby can't get to the most advanced stuff until they have an appreciation for the circles and the squares. A lot of times, students, I've noticed in these advanced courses, they like to skip the things that they think is just simple and try to move on to the most advanced topics. And then once they get to the advanced topic, they notice that there are some things that they don't really get. But what they don't get is not the difficult information, it's the information that they kind of skipped along thinking that it was so commonplace. Just because somebody else can sing the song doesn't mean you can sing the song like that. You got to sing it. You got to practice singing it. Right? Or just be like in our church, if you forget the words, you just act like you're full of the Spirit, and fall out or something. And everybody get excited. Oh, praise the Lord! No, you just forgot the words. That's all you did. But anyway, I'm not supposed to say that, but I'm thinking it. Okay, now let's look at this one. Here we assume that the solution is of the form y equal to x to the m. So if that be the case, then this problem has a y prime and also a y double prime. So I need to find y prime. So this is going to be m times x to the m minus 1. Right? If you have y equal to x squared, what's the derivative of x squared? 2 times x to the 2 minus 1. Right? We don't know what m is, right? So we have to write that m minus 1 up there as an exponent. And then y double prime is m times m minus 1 times x to the m minus 2. So I go look at the equation and I replace the y double prime with m times m minus 1 times x to the m minus 2. Replace the y prime with m times x to the m minus 1. Replace the y with x to the m. So we have x squared times y double prime, that's m times m minus 1 times x to the m minus 2 minus 7x times y prime, that's m times x to the m minus 1. This is plus 15 times y, and y is x to the m. That's all equal to 0. Now, well, I'll write it out. This is x squared times m minus 1 times x to the m times x to the negative 2 minus 7x times m times x to the m times x to the negative 1 plus 15 times x to the m. That's equal to 0. Now x to the second times x to the negative 2, well, that's equal to 1. And then this x to the first times x to the negative 1, well, that equals to x to the 0. That's equal to 1 as well. So all we have left now is m times m minus 1 times x to the m minus 7 times m times x to the m plus 15 times x to the m is equal to 0. Now, if those exponents and those variables don't cancel out like that, and you're trying to solve, then, man, you better run. No, well, the solutions for something that's different than this, where I told you these problems are rigged, where if I couldn't cancel out so readily x to the second, x to the negative 2, and so I'm going to get different values with the differential equation, then either there's a model that exists out there that I want to mimic for the solution type, or you have to solve the problem by power series, which that leads into what we call Fourier analysis or Fourier series. And there's a chapter here, chapter 6, that deals with those type problems, the problems whereby I have no other method of solving this differential equation other than to use power series solution. So what am I saying? What did I just say in that statement? Let me give you the philosophy behind it. The philosophical statement is this. Everything that we're doing in math, in these classes, everything that we're doing, the solution already exists. There's a model out there for the solution. So you're just trying to match up from the problem to a solution that's already out there. So even though you're trying to figure it out, that solution is already known. Right? I'm trying to connect to make sure that the problem that I'm given, I can find the model by which to solve this problem to get that solution. But what happens when you have a problem and, one, you don't know the model, so you don't even know the solution or the solution type. For these problems here, the solution type is like y equal to e to the mx. So I use that as my base to solve for the solution. Or y equal to x to the m. I use that as my base to solve for the solution. But what if you don't have anything like that? Wow. And that's when it gets difficult. That's when it gets challenging. And that's where you come in as a young scientist or engineer. Because that's what is going to be the problem when you're on that job site. You're going to be given a task. And there might not be anything out there that exists in terms of how to produce whatever you're trying to perform on that job site. Right? So you do your research, you collect data, you study the data. And sometimes the data may suggest a model, sometimes it may not. Well, we can factor out x to the m, right, from all three of these expressions. X to the m comes out. So I have here m times m1 minus plus 15. That's all equal to 0. Make a assumption up there. I didn't. Here, we assume that x is on the interval, open interval from 0 to positive infinity. So we assume that the solution is positive and that the solution is not 0. No. Now, why do we do that? Well, it's easy. We make this assumption up there I make this assumption because if I don't make that assumption, then you have to actually solve for x to the m by itself. But if x is not equal to 0, then x to the m is not participating in the solution, but what's in the bracket is. So here, since by the assumption x is on the interval from 0 to positive infinity, that really means that is x is not equal to 0. We get a lot from that. X is positive. Also, x is not equal to 0. Then this implies that m times m minus 1 minus 7m plus 15 is equal to 0. Because if I got something times something else equal to 0, and if you tell me that one of these guys can't be equal to 0, well, the other guy has to be, to make this that something times something else equal to 0. Right? So here we have m times m minus 1 minus 7m plus 15 is equal to 0. So this is m squared minus m minus 7m plus 15 equal to 0. This is m squared minus 8m plus 15 equal to 0. We can factor this. M minus 5 times m minus 3 equal to 0. And so we get m equal to 5 and m equal to 3. So two solutions. Y sub 1 is x to the 5th, right? Because the solution type we said is x equal to x to the m. And y sub 2 is x to the 3rd. And again, you can check those and check them one at a time, and they work out. Any questions? Let's look at some mathematical models. And got a couple problems over there that I would like to work before we leave today.